Okay, I'm coming back from ESSERC business trip, Munich, Germany, and I spent quite a good time there and listened many important presentations. But due to my personal issue, unfortunately, I cannot make the offline lecture for lecture 5. That's the reason why I'm pre-recording once again this lecture 5. So sorry for any inconvenience, and whenever I am ready for offline lecture, I will immediately come back to the offline lecture. So this lecture 5 is devoted to the scaling still. So in previous lecture, lecture 3 and lecture 4, we just set up the environment for our later exercise. However, I will just come back to our original discussion about MOS scaling. Okay. So now 16 years have passed. Uh, well, now we are in 2014. This is already 11 years ago from present. However, once again, also it has 16 years later from 1998. So at that time, the state of the art was not a planar MOSFET, but a FinFET. So actually, Intel's 14 nanometer technology is not their very first FinFET technology, but it is the second generation of Intel FinFET. And I will explain it a little bit further. Uh, uh, but Another observation is, although it is second generation of Intel FinFET, but in this class, Intel's 14 nanometer is not the first one. 1 year before, so TSMC announced their 16 nanometer technology. So 16 nanometer technology and 14 nanometer technology are regarded as in the same class. Hmm, well, so it just shows that around this time now technology leadership has been changed. However, at that time, nobody actually did, uh, or at least myself, I was not able to recognize it quite clearly because still Intel's 14 nanometer technology was superior to the TSMC 16 nanometer, but later it changed quite a lot. And here we introduce a structure called as a fin, and this is called as a fin, and this is called as a fin. Okay, there are two fins in this case, and distance between these two fins, the minimum value we can have is typically called as pitch. So it means that 42 nanometer fin pitch means that in this case we can separate these two fins by amount of 42 nanometer. And we have a different length scale. So CPP here, contact gate pitch. It is a different name of CPP, contact poly pitch and contact gate pitch. They are the same one. Um, Actually, since nowadays no one is using polysilicon as a gate contact. So contact gate pitch is more accurate expression. However, um, still people say CPP. Okay, so in this case, contact gate pitch is 70 nanometer. So, question is, now we have two different length scales. One is thin pitch and one is contact gate pitch. Previously, when we consider quarter micron technology or 180 nanometer technology, more or less the x directional length scale and y directional length scale, they were measured in a single number. There was only one number. However, you can easily understand already there is a certain difference between this channel directional and perpendicular to the channel direction. So fin pitch is 42 and contact gate pitch is 70 nanometer. We will use this observation quite a lot because nowadays the contact gate pitch is more or less given to certain number, and what we can do is more or less related with this number. Actually, not exactly pitch, but we are trying to reduce the number corresponding to or closely related to this number. Okay, so since miniaturizing the structure into bidirectional, x directional and y directional becomes too complicated. So that's the reason why now they introduce independent scales for x direction and y direction. That is one thing. And gate length is 20 nanometer. So you remember that in former technologies, so around 200 nanometer or 180, actually the gate length was even shorter than the name or the number shown here. So although it says that 250, but it was shorter. But now, when you have a look at these numbers, although we call it as 14 nanometer, but gate length is now 20 nanometer. So nowadays, people say that 3 nanometer technology, 2 nanometer technology. However, our gate length is not actually 2 or 3 nanometer. So it is much longer than that, about 10 something nanometers still. So the trend has been reversed dramatically. And here you can see that the area of SRAM, SRAM area is scaled quite a lot. So previously it was almost 10 square micrometer for our the quarter micron technology, but now it means that 1 decade, 2 decades, and yes, almost about 200 times reduction of SRAM size. So when we consider this number and 250, there is around about 10 or not 20, but times difference. So scaling up to this point, the SRAM scaling works quite good. So that was happy area. But nowadays, the scaling of SRAM itself is almost saturated, and even in my business trip to EIC, I could see many, I was able to hear many questions to TSMC guys. SRAM, is it really further scaled or not? So the answer was cell itself cannot be scaled quite a lot, or at least very difficult, but by reducing other parts, so effective area of SRAM can be further scaled down. That was their answer. Okay, So also let's have a look at this transistor IV characteristics from Intel's IBM paper. And you can see that this number ID is also written as ampere per micrometer. Or so actually it should. I think that there is something wrong. So we must have 10 to the minus 3 somewhere. Okay, so this is corresponding to micrometer, milliamp per micrometer. And here we have the number 1. Yes, so we must remember that state-of-the-art devices have the numbers, uh, the on current around 1 times milliamp per micrometer. Of course, the number 1 or 2, that really depends on the situation, but the number, but anyway, we must remember the order of magnitude or its rough value. And one very important observation is now M MOSFET and P MOSFET shows more or less comparable on current. Well, previously, when we remember the values for quarter micron technology, there was more than twice the differences in the N MOSFET current and P MOSFET current. But now this difference is much smaller. So the textbook lessons like the size of NMOS and PMOS should be about 2 to 1 or 3 to 1. That is a little bit old-fashioned trend. Okay, so now let's go to the next part. So this figure is taken from Synopsys uh, newsletter, and it is just visualizing 3D structures of a FinFET transistor. So previously we have seen the fin, and where can you find the fin? Here we have a fin, and this is corresponding to this one. Actually, what we are currently looking at in this slide is a cut of this three-dimensional structure for that plane. Yes, then you can see that a fin surrounded by the gate oxide. Then what you can see is this is the fin and covered by this oxide, gate oxide, and also filled with metal. In this case, intentionally, they did not show the metal, so that's the reason why we don't have metal, but this part should be covered with metal. And when you have a look at this one, or come back to the more realistic one here, now you can see that uh, even though if we don't count this entire height, but when we consider only this effective part, still it is tall and narrow structure. So now you can understand, although it is called as sometimes by Tri-Gate by Intel, but when we consider the coverage of three different gates or phases, you can easily understand this phase is quite long, and this phase is equally long, and this side is quite short. For this Intel 14 nanometer technology, it is known that its fin width in its narrowest part is about 8 nanometer. So this is just 8 nanometer, and this is much taller than that. So although FinFET is called as Tri-Gate, however, actually it's like a double gate. These two side gates performs the most important role. Of course, it is a top gate support additional charge carrier control. Then, natural question is then why we prefer to have the double gate structure over the single gate structure. Everybody in this classroom understand it is only due to the better gate controllability. By changing the gate voltage, we can more efficiently control the inversion charge density. Yes, we all know it. But if we are asked to explain it, then how can we explain it to other guys? So we need some just not just plain English, but we need some formulation or expression. So based upon that expression, we can share our idea more clearly. Here, we have other structures besides this fin, and we have a spacer and source and drain, but these will be discussed in our later lectures. So for a while, we can just skip this part. Okay, so the remaining part of our lecture will be devoted to some expressions for so-called natural length. Okay, for that purpose, we need to review our previous course, VLSI devices. So if you are interested, then please watch the video for this VLSI devices course, lecture 16, 17, and 18. Okay, almost 3 lecture hours or the lecture slots sessions were devoted to this single topic, so it is quite important. However, I wanted to just make a short review on this topic because we have to also follow similar work today. So now, what we wanted to do is when we have a certain structure, MOSFET structure, we wanted to see the effect of drain voltage on the channel potential. That is the point. Why we are interested in that impact? Because that describes more or less the dBl quantity. dBl is one of the most important quantity for short channel MOSFET, and we wanted to minimize it. So that's the reason why we wanted to see the impact of drain voltage on the channel potential, especially since that is more or less related with the shift of threshold voltage. We can do this kind of approximation, sub-threshold regime. So if we have the parallel shift of IV characteristics in the sub-threshold regime, then it is interpreted as the shift of the threshold voltage. That's the reason why we can assume this sub-threshold regime. Okay, in this case, the Poisson equation can be simplified greatly because in general, Poisson equation should consider the contributions from holes and contributions from electrons not shown here, and contribution from p-type substrate for this box. Of course, if we consider these points, then obviously we have to consider donor density here, but we wanted to confine our consideration only for this box shown, silicon box shown here. But anyway, in general, we have to consider 3 different considerations: hole contribution, electron contribution, and proton contribution. But since we are currently assuming the sub-threshold regime, so we can easily remove or neglect the electron contribution. Good. And also hole density P here is a nonlinear function of electrostatic potential phi. However, if we also consider only this box in corresponding to the depletion region, then also due to the depletion phenomena, we can safely neglect this hole density. Then simply means that our original Poisson equation considering electrons and holes can be simplified as this just constant source term. Okay. That was one simplification, but that was quite reasonable. And when you go to the next step, then the potential inside this box is determined by boundary conditions. And these boundary conditions determined by the gate. Gate changes the potential in this line, and source changes the potential in this line, and drain also changes the potential in this line. Of course, here we have substrate, so this part is determined by substrate bias. So different contexts introduce different boundary conditions here and there, so we must consider them all. But fortunately, this system is now linear. There is no dependence of this source term on the electrostatic potential. So now we can try this kind of a solution. The, the solution obtained by solving several different equations and sum them all, and they have different source terms and boundary conditions. In this case, the one controlled by the gate contact is shown here, and the one controlled by the drain contact, source contact is shown here, and the one obtained from the drain voltage shown here, and this one is corresponding to the substrate. So that is the consideration, and of course, the overall MOS behavior is governed by this long channel expression, but our concern is what will happen if we reduce the channel length, and particularly what is the impact of a drain voltage on the channel potential. So we are interested with this function, so we will use this one. For this one, the boundary condition we wanted to have is now in this part we apply the potential determined by drain voltage, and other terminals impact are considered by different other accompanying potentials or solutions. So we will just consider 0 and 0 and 0 for these three sides. So simply speaking, now the system becomes much simplified. Also, here we have a constant source term due to the depletion charge, but that is also covered by this long channel part. So, simply speaking, the equation for our function u sub r, which describes the impact of drain voltage on the channel potential, just satisfies simple Laplace equation instead of a Poisson equation. Difference between the Laplace equation and the Poisson equation comes from this source term. When it is 0, then it is called as a Laplace equation, and if it is non-zero, then that is called as a Poisson equation. So we can just solve the Laplace equation, and boundary condition is now we have a certain voltage here and 0, 0, 0. That is the situation we had in our previous lecture, VLSI devices. And now, when we try to find out a solution of a Laplace equation, it is done in this way. Our use of R solution is decomposed into two terms or product of two functions, x directional component and y directional component. Of course, there is no guarantee that this decomposition x and y is successful, but we try and it is a certain solution. Then once we can find the solution, then that becomes the solution. Yes, when we have this product term of x directional component and y directional component, and just insert it to our Laplace equation, then we will have this form. Yes, but in order to have a Laplace equation, that should vanish. But if we assume that if second derivative of x with respect to x is just having itself an negative 1 over square lambda, and if we also assume that second derivative of y function with respect to this small y is the same function and with positive, that's important here, positive 1 over square of lambda function, then please just to consider this condition. This one becomes x and minus 1 over lambda square. And this one becomes y times plus 1 over lambda square. They become the same except for this negative sign. So quite obviously this one becomes 0 when we have a certain condition shown here. And what is this? This x function, when we take the second derivative of this x function, it becomes itself. And we have a negative values, eigenvalues. And it has positive eigenvalue with respect to the second derivative. Sinusoidal functions satisfy this first condition, and exponential functions or combination of exponential functions shows this expression. So simply speaking, the vertical x-directional variation is given by this x function, and y-directional variation or lateral directional variation is determined by this one, but they share the same length scale, lambda and lambda. If this lambda becomes larger, then of course this lambda should be larger because they are the same. It means that if we have a certain structure with long lambda case, then our potential solution just varies quite smoothly and affect in a long range. We wanted to minimize this lambda because it is directly related to the length scale of our y-directional function, channel directional function. We wanted to minimize lambda value. That was the most important lesson from this L16, L17, and L18 of our previous lecture course, VLSI devices. So, vertical variation in MOS direction and lateral variation along channel directions are coupled. So, if we wanted to have a good short channel immunity, then we have to reduce the size of a vertical structure. That was our achievement. And now, let's go to the double gate structures. In this example, we wanted to discuss two different structures. They share the same silicon thickness. Yes, they share the same silicon thickness, and there are two gates, one gate metal and another gate metal, one gate metal and another gate metal. However, the difference is this thickness. This is oxide layer and this is oxide layer. In this double gate expression, we have the same oxide thickness, and now they are symmetric at this midpoint. So now we can consider only this positive part due to the symmetry, and we have effectively two gates metal, top and bottom. The second one is almost a single gate, although we have the T silicon as a thickness of silicon layer, but the thickness of this bottom oxide becomes too thick. So, although we change the voltages in the bottom contact, but the field felt by this bottom surface becomes quite small because this change, voltage change, should be divided by the length scale, bottom oxide thickness, and since it is so thick, so the contribution from this bottom gate is negligible. So in this extreme case, we assume that the electric field vanishes at this point. So in order to make our expressions quite simple, is intentionally we set this coordinate system. Silicon in this case starts from 0 to T silicon, thickness of silicon, and in this case we start from minus half T silicon to positive half T silicon. So that is the case. Let's try to compare these two structures. Our goal is to calculate lambda values for these two, and hopefully maybe this one has a shorter lambda than this structure, almost a single gate. Then it reveals that double gate structure has a better short channel effect control over single gate case. We will see it from now on. Okay, the boundary condition is shown here. At the boundary between silicon and silicon dioxide, the continuous quantity is not the electric field itself. Instead, the displacement vector should be constant. Our normal component of a displacement vector should be constant. So here we assume that this U sub R is a homogeneous solution induced by the drain voltage. Then we have to have these two cases for double gate structure and single gate structure. Please note that here we have different positions because for double gate one, this is top surface, and single gate one, this is top surface. But anyway, this vertical directional electric field times permittivity. So this is the displacement calculated at silicon side, and this one is corresponding to the same displacement value evaluated at oxide side. So at the same point, interface point, these two evaluations should give the same number, so that becomes the boundary condition for our interface points. Please note that these two expressions are intentionally assuming only the vertical component. Vertical means that x-directional component. Of course, we can have also contribution from lateral potential difference along channel direction. However, that is intentionally neglected to make our discussion easier. Okay, so however, it is good enough for approximation. Okay, so now you understand, although position is different for this individual case, however, they share the same philosophy. Displacement evaluated at silicon site and the one evaluated at the silicon dioxide side should be the same. That is shown here. And when we just insert the expression of use of R, which is decomposed into X and Y, then simply speaking, the only derivation is related with the X directional one. So there is nothing related with this Y function. So Y function can be safely eliminated in both sides together, and we have the same expression for single and double gate. That's it. The difference comes from their boundary, hidden boundary. So due to our symmetry, in the case of a double gate, we must have cosine x over lambda. This should be the form of x. Of course, here we have a certain coefficient a for normalization, but for y, just to neglect it, we wanted to have the functional form. And in this case, in general, we can have a sine function too. But if we have any kind of a sine function and it has non-vanishing electric field at x equal to 0. But when you come back to our structure, and this is corresponding to x equal to 0, and this structure is really symmetric about x equal to 0, so the electric field should vanish at x equal to 0. So sine function does not allow vanishing electric field at x equal to 0, so we did not include this sine function. Now we only have a cosine function and just dump it into our boundary conditions. And now here we have a colored one, highlighted one, and this number 2 is occurring because we are considering half structure, not entire T silicon, but the upper surface or upper interface can be found from just T silicon divided by 2 away. So now we have this expression, and here we have sine and cosine. They can be combined into tangent, and here we have another number. Let's have a look at an example, concrete example. And in this case, silicon thickness is given as 5 nanometer. Is it reasonable or not? So if we consider, for example, 14 nanometer Intel technology, then actually this number should be 8 instead of this 5 nanometer. However, nowadays, if we consider 3 nanometer or 2 nanometer technology, this 5 nanometer is quite a much reasonable number. And TOX, of course, effective thickness, EOT, and this one is set as 1 nanometer, and this 1 nanometer is a little bit well, a little bit thicker than the realistic one, but well, for a while, just to use it. And assume that silicon's relative permittivity is 3 times larger than oxide relative permittivity, and that is true, regardless of the technology. So in this case, now we have 5, 1, and this number gives us just 1/3, and this left-hand side term is drawn as a function of lambda, and that is written in this blue curve. And this orange curve is corresponding to the right-hand side. And of course, when these two graphs are meeting together, that is corresponding to the value of lambda. For example, yes, this is the corresponding lambda value. You can ask me this question. Okay, we can find multiple lambda values. Here we have lambda, and here we have also another lambda. There are many lambda values. Yes, you are right, but this shorter lambda value decays quite rapidly because this lambda is used to describe the decaying rate of our channel directional exponential function. So we wanted to have the we wanted to have rapid decay. So this lambda should be short. So that's the reason why in this case, in order to talk about the worst case, we must find out the largest lambda value or the longest lambda. So although we have many other candidates, but they are not practically important, and this one is the most important one. And in this case, we obtain certain number close to 3.1 nanometer. Okay, so since we have the lambda is corresponding to 3.1 nanometer, it simply means that our drain voltage decays with the length scale of 3.1 lambda. So, for example, if our channel length is just 5 nanometer, and it is even shorter than 2 times lambda, so impact of our drain voltage can make a significant one on our even source side. That is not desirable case. Okay, this is the double gate case. Then now let's quickly go to the single gate case. Oh, but again, due to the boundary condition at x equals 0, in this case also at x equals 0, due to thick bottom gate oxide, then we must have still cosine function. Don't be confused why we have the same function, because we intentionally introduce a shift of our points. Now this is corresponding to x equals 0. Yes, it becomes our evaluation quite easier. So in this case, still sine function is not possible. So we have the same function, but difference is now the evaluation should be done at x equals t sub silicon, not half of it. So when we insert it, now we have it highlighted here, instead of previous number 2, now we have just number 1. So when we just manipulate it, now we have 2 different terms, left-hand side term and right-hand side term. And right-hand side term shows the same one, but now this tangent function has a different argument. So now we have a different shape. And for the same values, now the largest lambda value is corresponding to about 4.9 nanometer. Means that for this single gate, the lambda is longer, so for channel length is given, then it becomes weaker to the drain voltage excitation. So that is the case. So that's the reason why, let me just summarize our discussion. As you can see here, although the silicon thickness is the same, but due to the existence of the second gate or bottom gate, now the function solution along this vertical direction is changed greatly. So that's the reason why their lambda values shows some differences. This one and that one. So this is short lambda for double gate reveals superior short channel immunity of a double gate case. And finally, this is the final page of our slide, or this is the final slide of our lecture today. And these expression shown here or there is a little bit difficult to evaluate it because this one is related to the nonlinear function, tangent function. So although not perfectly correct or accurate as shown in our previous example, but this tangent function is frequently approximated as itself under the assumption of a small input argument. Unfortunately, it is not always the case, but well, anyway, just to do it. This tangent function is just approximated as argument itself. And now here we have a lambda, and the same lambda is shown here. Then this lambda is gone, and this term goes to the left hand side and take the square root of it. Then now we will have quite well-known expression for this lambda, so-called the natural length. In this case, here we have the ratio between permittivity and product between silicon thickness and oxide thickness. And most importantly, here we have the number n, the number of gate terminals, single terminal or double gate, yes, single gate or double gate. Depending on this one, if we introduce a double gate, then it means that our lambda value is much smaller, approximately 1.4 times shorter, and that is quite a big deal for this scaling consideration. Once again, this approximation is obtained from very crude steps approximating this tangent function as just a linear function, identity function. And this expression yields 2.7 nanometer and 3.9 nanometer of lambda for these two devices. The exact number was 3.1, 4.9, so it is just predicting the different numbers. However, the trend is important and it clearly shows that still double gate structure is much better than single gate structure. This expression is quite important. So it provides us in order to control the short channel effect, we must reduce the thickness of a channel material. So it is the main driving force of introducing different materials, especially 2D materials, into our SIM, VLSI devices SIM. If we can reduce this silicon thickness, in this case, channel material thickness quite a lot, then this lambda can be shorter. Then we can further reduce the short channel. Uh, we can reduce the channel length. So even in this ESSDIC in this year, we had a very good presentation about this topic. This topic. So this is quite a fundamental uh, expression we have to remember. Okay, so that's all for our lecture 5. And once again, sorry for this pre-recorded video. And I hope that we can meet once again in the classroom quite shortly. Thank you for your kind understanding and see you later. Bye.